Okay, well, let's remind ourselves, okay, we're in 3 dimensions, and when we're doing particle in a box, you had a homework question with a 3D particle in a box. It's just so simple that I just relegated that lecture to 10 minutes of an extra hour, right? So here's the Hamiltonian. The solutions are sine nx, sine ny, sine nz. You get quantum numbers. You get the ability to have degeneracies as a result. Yeah, this was, deceptively easy, but then when we started going to rotational, we start with cylindrical coordinates, we do the 2D rigid rotor. We're in cylindrical coordinates, and as you are doing on your homework right now, the transformation of this to this is really pretty awful. I mean, I had you do it in tiny steps on the homework, and now also recall that I actually just straight up word questions 1 through 5 on the video that's on the resources section of the handout. And so, now the other things to remember about the 2D rigid rotor, remember that the wave functions, okay, now I have a handout showing that the solution is separable, and so you can look at that. Even that is relatively complicated. Like I say, I was doing that to this, and I was going to make that like the hard question on the test, and I just found it took me 2 pages to do it. So I'm going to just have that for a handout, and that'll complement what I'm doing today in 3D. Okay, now recall that this guy ends up just being a constant because it's the rigid rotor, which means that we tied, the particle is always an electron, it's just called an electron. I guess it could be a neutron. It's an electron, and it's on a string, so the R is always, and let's just say it's 1 nanometer. I mean, it could be half nanometer, but whatever. Let's just say it's 1 nanometer. Things are always small and light, right? Because otherwise quantum doesn't really show up so well. Okay, now when you do that, remember that wave functions squared, not wave functions. Wave function squared are probability distributions. When we write them in terms of x, y, z, r, theta, phi, they tell you where the thing is. But the reason that the radial wave function just basically, it's just 1 nanometer. And that sounds like a weird wave function, but that actually is true. It's just a constant. It's because there's no information. I mean, it's just at 1 nanometer. So the wave function just becomes a constant, and that means that these terms get wiped out, and then we're left with a second order differential equation where we have a normalization. So remember that I started out solving this wave function in a snarky way by taking a particle in a box and flipping it over on itself, get you kind of calibrated to what it should look like. And we actually legit did solve the correct wave functions. We figured this out. But a better way is to impose to do it mathematically, not with pictures, to be blunt. The way to do that is to say that the wave function at angle of 0 and an angle of 2 pi have to be smooth and continuous. And when you do that, you find that EBIM phi is the correct wave function. The boundary conditions also tell you that you've got this deal, of course. And again, I'm still just reviewing. The normalization constant is just from normalizing it, so that there's not much to that. I did that in class, you did it on the homework. And so then you're pretty much done. And now I'm kind of blanking out what I had to do on. I think last lecture, remember there's all kinds of crazy nuances to this. Remember that sine and cosine don't work because you're allowed to know whether it's rotating right or left. It is allowed to not rotate at all. Really, it's a lot more like a free wave really than a particle in a box. So I like starting out the particle in a box because it kind of gets you the idea of the wave function like folded in on itself, that the tail, the head has to bite the tail, which is really important. But after that, really it's more like a free wave, including free waves can also not move. And then it also, the other difference is it can't be sine or cosine. So that's where it's unique. But it's, it should be unique because it's unique. So I might have some short answer questions on that on last lecture. Sorry, that was Friday first lecture, which are posted, by the way. Okay, any questions? Okay, so now of course when you did cylindrical, right, there was no z. There is no z, it's 2D. And you saw what a Bisnocker this is to create. Now put in z. Now when you have z, even the coordinates, you remember that what x was r cosine, something like that. Well, now x is r cosine sine or sine sine. I don't know. Anyway, it's even more even the x's and y's are more complicated. Then you've got to do the derivative. Then you got to do the double derivative, and then you got an extra one, right? So you know that. I mean, it's just the world's greatest exercise in organization, right? Now, you're doing this on your homework. It's not that bad. It's kind of a lot. In 2D and 3D, I started writing it one day. I thought I'd put a handout, and I realized I was going to be writing 20 or 30 pages of algebra, so I'm not doing that. I'm pretty sure I can do it. It's just I don't really have that kind of time on my hands. That's like 2 or 3 days of algebra. So now again, I have you do all that because I want you to get a feel from that. I don't want this to be magical, from here to here to here. I don't want it to be magical. Hopefully I've accomplished that. Also, I want you to just get used to all these sines and cosines and 1 over r's and 1 over rdr, blah, blah, blah. The more comfortable you are, then, that's good. Also, it's kind of cool. You can do this, right? I mean, look at this damn thing. You can do this. That by itself, I think, is kind of cool. And do what with it? All right, so for rigid rotor, of course, we're going to assume that this is a constant. So there's no information. So the derivatives with respect to r are gone. But remember, r is still like half a nanometer. I don't know. The thing is on a string. So this guy, you don't just get rid of the r's, you get the derivatives of r, because remember, the wave function is a constant, and that makes those derivatives 0. All these terms get wiped out, and we're left with just this part. Now, on your homework, I have you do some things with this again, not just deriving this thing, but I also had you operate on this thing with some wave functions, again, just to get you comfortable. And this is often given a little symbol, just because writing this stuff out, it's, what did I call it? I called it in the homework. I gave it, it has a name, a Gaussian or Lagrangian or something. I forgot. Anyway, they give this thing a name because just to make it easier to write down, basically. What do I want to say? So, all right. So the next thing is to, as usual, I'm going to just start writing down wave functions. The second order differential equation solved in 1782, by the way. It's still over my head. So, I'm just going to give you the answers, but I explore every other facet. So I really want to dig deep into understanding everything, because I'm going to table the actual bloody, awful second order differential solving thing. Because to be blunt, when I read these, I have them in a textbook. I can read them, I can follow along. It's not too bad, but I also mentioned it's also a couple of days to do that. So the thing is, what I want to do is, again, what is all the things I could possibly do short of actually solving it, which is to show that it is separable and to do separability. Okay, you get a couple of lessons in this. Now again, I got to remind you that I do have a question like this on the test, except that it is way easier than what I'm about to do. So remember that separability is when you have some Hamiltonian, you apply a wave function on the left and you divide by it on the right. And what you end up with is some terms plus some other terms where all the variables for one thing, like all the x's are here and all the y's are there. So that is how you show separability. And what you end up with is that this is a mini Schrodinger equation, number 1. And this is also a mini Schrodinger equation, number 2. So that's how you solve these. It's very important to do this to show that you can, create wave functions that are like I was using, I think, x and y as an example. So it's very important to show that you can do that because it makes solving it tractable, because otherwise maybe you have to use a supercomputer to solve it. So that's when you're doing that, that's called a numerical solution, by the way. What you're seeing are all analytical solutions. That means that the answer is always either I phi or either minus I phi. When we get done with the hydrogen atom, there are no more practice problems that can be done analytically. They're all done numerically. That means that there's a solution, but the solution is in the form of a gigantic terabyte table of numbers. So when you apply these derivatives to the table of numbers, you can still, you can calculate derivatives from a graph numerically, but that's how you have to do it. Anyway, so now I'm going to do that with this thing here. And of course, what I'm going to do is we've tabled the radial part, and we can still show that it's separable. And I do that on the handout, but if we've magically, remember that this problem is a little bit, it's a good introduction, but it's silly because there's no way to hold an electron on a string and keep it fixed, but regardless. So again, let's forget the radial. What I'm going to do is show that, or I'm going to prove that I can write the wave function in terms of a separated solution of two angles. And, oh God, what do I want to do? Okay, so I have to do some algebra beforehand. You see, just heads up, this is going to be a lot funkier than you think, by the way. You're going to see something very weird about to happen. And I never can quite get over this, but this is how it is. Okay, so first thing, so there's the wave function. We're going to do separability. The first thing is multiply. So first I'm going to multiply by the 2 mass. Of course, we're going to have mass times r squared. We're going to have mass times r squared, so we're going to have our moment of inertia. That way, m's and masses won't get confused. I've talked at length about that.
Are those supposed to be 2 different angles?
What's that?
Are they both phi or are they 2 different angles? Okay.
Theta, yeah. Problem with not PowerPoint, right? So I do that. Thank you for pointing that out. Oh, Jesus. Usually Mondays are my good days. Okay, so all right, I just have to follow my notes. Okay, so I'm also going to multiply. I'm going to multiply by sine theta squared. So remember that these guys are gone, and I'm going to multiply by sine squared. I'm also multiplied by 1 over that. So 1 over this, 1 over that. And so just look out for that. So I want to point that out because if you get confused about some of my algebra, you'll get totally lost at the first step. So I really don't want that to happen. Okay, so what have I got? Here, I'm not going to follow my notes. I'm just going to do it. That's probably a bad idea. But I'm just going to try to write it down because I'm actually already not following my notes. Okay, so this is the part that's like 2D. And I know that that's very related to the angular momentum in the z direction. Because remember, when you're in the xy plane, your angular momentum is technically pointed up in the z. So this is oddly enough, the angle, remember the angle tells me about x and y, but I really call it my z guy, because the angular momentum is actually in the z direction. And theta, which is the angle along z, is actually the vice versa. It's just kind of funky. Okay, so anyway, so I've got that. Now I'm going to multiply it by a sine, hopefully I won't get this wrong. Okay, so I've got that deal. Okay, now I'm going to multiply, I've already multiplied by sine squared, so I've got sine theta squared. So the reason that sine theta squared is gone is because I multiplied by it. Also the minus h bar over 2m. Okay, so theta, notice that this is, that the sine theta squared only operates on the left side. And I've got and it may permute the way I write these because I'm a jackass. Okay, since I'm operating on the Hamiltonian, I've got sine theta squared minus 2 times mass over h bar squared. Now, you may be thinking, why am I writing anything? Because you're used to an operator wave function. I actually have to include the I forgot 1 over r squared. You see that? There's that r squared there. R squared. You see, I'm actually including the eigenvalue E, right, so operator, wave function, E wave function, I'm actually including that part, including the right-hand side, and then I've got the wave functions. Gave myself just enough room, and that doesn't look good. Okay. Okay, so again, right, kind of, all right, next bit is to divide, now let's see if I can follow my notes. Okay, I'm going to do 2 steps of algebra at once. I am going to go ahead, you see this guy is stopped by this wall, but this guy comes through. But then I divide on the left by, I divide on the left, so I write that on the left with the wave function in the separated form. Okay, now, knowing that this one is stopped, this one's come through, but it ends up being divided out by the wave function in its separated form. So the phi guy is still here because the phi guy that was operated on is still stuck. It's still stuck at the operator. Okay, and what's nice is that that looks separated. So I've got that right. Okay, now, same deal here. These are walls of theta. So theta gets stuck, but phi passes through. Phi will pass through here, but it'll be divided out. So that means I end up with sine theta over the wave function of theta. Again, because the theta guy is stopped by this theta wall. The derivatives, which are walls.
Theta for the first one. The first paragraph.
Huh?
Shouldn't that one be theta? Before it. Before that.
No.
No theta cancels.
No, theta comes through and then it gets divided out.
Gotcha.
Right, yeah, exactly. Right, yeah, you see, that's exactly what I want to do. You want to confuse, you want to permute them, don't. Right, just be very careful with your algebra. I probably should not be skipping, I'm doing 2 steps at once. I probably shouldn't be doing that, but I'm kind of stuck now. Okay, so now what I do is, I'm actually done with this part here, but what I'm going to do is I'm going to bring over this deal, sine theta squared. I've got 2i. Now I is now mass times r squared, so you should hopefully remember that. And of course I'll make sure that if you get confused, I don't care about those details. If you make some kind of mistake on the exam about that, I'm not going to care at all. 2ie over h bar squared. You notice how we always seem to have 2 times something times mass times energy over h bar squared. So that always seems to want to show up. Okay, and again, on this term, when we divide by the wave functions, they just get wiped out. Now it's equal to 0. Okay. Now, this is the part I told you. So nice, it's a little bit easier. Now, I know I did 2 steps of algebra. It's a little bit easier. This is the part that gets ultra weird. Okay, so this is, remember, it's like my z component. The r is fixed. This is like the projection, this is the angular projection in z. Remember, it's actually the xy part, but the j is in the z direction, so I call that my z guy. And it's a projection, right? This is the z component. This was all you had when we're doing a 2D rigid rotor, and now it's part of something else now that we're in 3D. I mean, how could it not be? We had to add a dimension, that means add a variable, the theta variable. Here's the part. Now, I'm a little pissed at this, but I guess it's true. I'm thinking I just don't know enough math. But here's how you proceed next. You assume that you already know the answer, which is e to the I m phi. And don't worry about the normalization constant. This normalization constant will get wiped out. We don't need to worry, follow the normalization constant in this case. So anyway, so we assume that we have the solution. Now this kind of pees me off a bit because I don't think when we're doing math solutions, you're supposed to assume anything. So that bothers me, yet here we are. Okay, so, but now in terms of like, this is the Z component, the Z projection, I think a justification is, you know, if I get a ball and I throw it in the X direction, I have an equation that describes that, but if I give it a little bit of a curve to the Y, you can still say that it has the same trajectory in the X, you know, the X projection is still the same because I gave it just as much energy in that direction. If I angle it off a little bit left or right, and that's this part here, it actually doesn't affect what happens in the component in the X direction as long as I give it the same oomph in that direction. I think that's the idea. So this was our solution beforehand, and really nothing's changed. It's still fixed to a string. It's still at 1 nanometer. You're now allowing it, basically what's happening is, now remember that before we're doing it like this, now all we're doing is we're doing a tilt-a-wheel. So that's, so now we're doing a tilt-a-wheel, but the projection into the XY plane is identical, so therefore you have the same solution. That's the idea. Okay, now if you do that, let's see what happens if you do the operation. Now you see why the normalization doesn't constant, because I'm actually going to divide by it. The double derivative of that is what?
Negative m squared.
Right, minus m squared. Right, I squared m squared, e to the I m phi, right, which is just minus m squared. Okay, so now I'm going to toss up the board and continue downward. I'm almost done though, because what I'm doing is I'm whittling this down into the smallest possible form, and then you'll just go from, oh that's crappy, you can't quite see that. Here, I'll write it down again. Now this is weird part number 2. So weird part number 1 is just assuming that the 2D rigid rotor solution is still okay. It's kind of justifiable because again, nothing really changed in terms of the projection onto the XY plane, but the negative is, and I don't really have a solution, and I think it's because I just don't know enough math. I don't think you're supposed to just presume things in mathematical proofs, yet that's exactly, to my knowledge, that's what's happening, but I'm also thinking maybe I just don't know enough. Okay, now don't forget that what I'm doing here is still going downward. All right, so now what I'm left with is, now I'm actually kind of confused where I'm at because this damn thing. Okay. So what I'm going to do is I'm going to bring this m squared, this minus m squared, over to the right. So, oh God, where am I at my own notes? Okay. Here's what I'm going to do. Sine, I'm writing this all over again. Now, one thing that's kind of cool about when you do the separability, you can unpack it back into a Schrodinger equation. It's actually really quite straightforward to see that you've actually got yourself a Schrodinger equation. Okay, so here's the idea. Sine squared 2IE over h bar. Is this right? Yeah, equal. Okay, so here's the thing. You know that when you've got these separated deals, each one is a constant, right? The guy on the left, because we assume a solution, the constant is minus m squared. The net constant on the right is 0. The solution is to make all this theta jazz, what?
M squared.
Right, m squared. Make all of this m squared. Sorry, my m's are weird. Okay. So now remember, and I'm praying, and I'll send an email reminder, when you do these types of differential equations, when you do these separations, you may find that, the whole differential equation is equal to a constant. When you separate them, you divvy up the constant into pieces. And it's not always straightforward to know how to do that. So what I've done is, I've taken the total, 0, and I've divided it into parts. One part is minus m squared, so the remainder is plus m squared. So the constants total to 0. Okay, then what I do is, and then my notes I don't, Okay, now that this is basically in the form, it's almost in the form of a Schrodinger equation, I'm actually done with this. Let me unpack it, let me just do some algebra. What I'm gonna do is I'm gonna bring the wave function, I'm gonna bring everything that's a constant, I'm gonna bring over here, and then multiply the wave function back out. So what I've got is sine theta, and theta. And notice also that the everything's theta. Everything's theta. That's also important. Okay, so I'm actually going to bring all these constants. I'm going to bring them on over here. And of course, I've multiplied by the wave function. Okay, so notice that it has very much the look of a operator. So this is some operator. This is the wave function equals to, and I'll use my old terminology, an eigenvalue times the wave function. I'm using kind of, I guess, yeah, you know what? This is technically a Hamiltonian. This is a Hamiltonian. So there you go. You see, so this is what I like about separability is, again, it shows that you can unpack that you can get the wave function into separated form, makes that easier. You end up with miniature Schrodinger equations. One of them happens to be, just assume we already know the answer, and then we're left with this one. Okay, now here's the part that's mega weird. This one decides the energy. You see? Remember, we have two Schrodinger equations. Because of separability, we end up with two miniature Schrodinger equations. One of them simply spit out minus m squared. That's all it did. Where's the energy? The energy is solved by the second miniature Schrodinger equation, which is just kind of odd. It means that this one is way more important than that one. Now, of course, they're still together. It's still one big solution into a product form, a separated form. But what you find when you start getting into these harder problems, and we're going to also see this with the Schrodinger equation, that as you add complexity, you end up doing more of the separability, but the energy always funnels down into like the last one. And in this case, the theta guy ends up being way more important than the phi one. And heads up, don't write this down, but after the test, when we do the hydrogen atom, this guy will also turn out to be pointless. And then the radial, we're going to have a radial wave function, and that's the one with energy. So that ends up being like the more important one. So there you go. And again, I want to emphasize that these are a bunch of constants. Okay, so what? All right, now you're left with this. So this is a second order differential equation that, guess what, was solved by a mathematician. Anyone want to guess when? Oh, I think I told you the wrong date, 1782. I think I said 52 or 92. Yeah, well, it was about right. 1782, someone solved this. Now, I don't think they had H in it, right? But they had this, some signs, and they had a constant. So that's how they did it. And all we have to do is substitute it. The constant is m over h bar, right? So it's very trivial for mathematicians to go through old textbooks and find that someone did the same thing once you realize that their constants are our constants. Okay, so what I want to say about this, and I have to get another board. So I'm going to go over some properties of the solution. Now on the homework, if you haven't done it yet, you are actually going to be working with that thing up there, and you apply some wave functions to it, and you show that it works. And again, we're not going to sit down and look at what's his name did in 1782 to solve it, because I'm sure it's 20 pages long. But I do have you look at the answers and verify that it works, and that's as far as I'm going to push you on that. Okay, come on, 10 minutes, that's still plenty of time. It's actually a tremendous amount of time. Okay, so number one, let's talk about the solutions. Okay, so solutions, they have a quantum number. Okay, so when this person was solving this, guess what? Infinite number of solutions. Just like a particle in the box has an infinite number of solutions. There's this one, which we know is the ground state, and then all the others are wavier. They have more nodes, and those are increasingly higher energy excited states. And remember, to the mathematicians, this doesn't mean anything, but to us, it has substantial meaning. So when they solved this, they said, oh, well, I've got an infinite number of solutions, and they have to have some kind of quantification, which was what we call a quantum number. We call it L. And they found, unlike our particle in a box, which goes 1, 2, 3, 4, 5, or our M quantum number, which is a little weird because it goes like -1, 0, 1, 2, anyway. This guy starts at 0, 1, 2, 3. They're always a whole number. It always turns out, I can't think of any, I know like 20 quantum problems, what we do here and what we do in grad school. You see some others in grad school. I don't know of any quantum numbers that aren't whole numbers. They're always a whole number for some reason. But then again, there's always one ground state, one first excited state, one second. I guess that kind of makes sense. Now another thing is that the energies always have the quantum number. Now remember, mathematicians just said, well, I have an infinite number of solutions, but to us chemists it makes sense. One of them is unique, it's the ground state, it's the one usually with no nodes. The others have nodes, that means more kinetic energy, that means that they're excited states. Now, if those have different energies, and they're distinguished by their quantum number, therefore the quantum number needs to be in the equation for energy, because they all have different energies and they're only differentiated by the quantum number. So anyway, so that makes sense. Now there is a subquantum number, which we already know. A subquantum number, which is M. Okay, now, by the way that they solved this is back in 1782. What they did was, when whoever, for whatever reason, basically solved that SOB up there, they had to solve the equation for M equals 0, M equals 1, M equals 2. It's just practically, and every one of them was different. And the person solved like 20 of them before he got bored or something. Anyway, so there's the subquantum number. Now, the thing is that it doesn't quite follow the same rules it used to, right? M used to be -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, anyway, blah, blah, blah. When you're in this situation, so what happens is, okay, so the person's solving this thing, and they're like, you know what, I got a solution, and there's L thing seems to be 0. What they find is that there's stipulations on the M. And what happens then is M is equal to -L plus 1, minus L plus 2, to 0, to 1, to 2, to L. Okay, so what happens is, let me unpack that. So the person is solving M equals 0. Right, now remember, what you have to do is you have to decide on an M value and then you solve it. When the person solved it, he found one answer. For M equals 0, he found L equals 0. Now, when he made M, for L of 1, for an L of 1, there were 3 answers. And they corresponded to M of -1, 0, and 1. When the L equals 2 solution kind of popped out, there were 5. -2, -1, 5 M's. -2, -1, 0, 1, 2, right? So it's an easy game to play. Now my question to you is, you actually know what those are. What's L equals 0, M equals 0? A what? Yes, it would be the ground state.
How many nodes do you have?
There'd be none. There'd be none. So the wave function, let's do this. L equals 0. And if I say L equals 0, M has to be 0. Again, because there's only one solution to this SOB if either of these are 0. Now, in that case, by the way, I'm jumping ahead, but the wave functions are just constants. And if you plot a constant in 3 dimensions, in 3 spherical dimensions, you just get a sphere. What do you call that? S. It's an S function. Right, you see? Okay, L equals 1. There's 3 answers. M sub L, we call them M sub L, by the way, because they depend on L. M sub L of -1, 0, and 1. 3 answers. P orbitals. If L is 2, there are 5 m's. -2, -1, 0, 1, and 2. D orbitals, right? That's where you get sp and d orbitals from. Right? Degeneracies, right? They're degenerate. They're degenerate because you're living in multiple dimensions. You can only have degeneracies when you're in multiple dimensions. Okay, so last bit is, let me write down some of them. And on the homework, you just apply some of the wave functions to that SOB up there. And you have to say like, okay, I tell you, this is the L equals 1, M equals 1 wave function, so apply it to that. You have to have enough horse sense to know that you plug in 1 into M squared, so you have to know to do that, right? And I think I spelled that out for you on the homework. So I didn't leave you hanging like that. I didn't want you, because if you set it up wrong, you're going to spend hours. And these are called spherical harmonics. And any of you heard that before? I know you engineers, you run into some of this stuff for other problems. Any of you heard that? Because I think it ends up being a solution. Kind of surprised. Seems like none of you have heard that. I think this is also comes up in some E&M problems, like what's the electric field on a sphere? Anyway, you run into these solutions for other things. Now again, if L is 0, M has to be 0. So when the person is solving the differential equation, there's only one solution. And it's just a constant, which basically makes it's just the normalization constant. And again, what's kind of interesting about that, when you plot a constant in R theta, VR is 1 nanometer, you just end up with a sphere. So there's not much to this. Okay, L is 1, you've got 0 and plus or minus 1 for your M. So again, when solving this thing, and the person's doing the L equals 1, there's 3 natural answers. And of course there's always a normalization constant. And there's this one. And then there is a sign. There's actually a pattern to this that I don't think is part of the solution. It's not like how they solved it. But so for, now I'm doing this in a certain order. So M equals plus 1. The z part is e to the I phi. For m is minus 1, it's e to the minus I phi. And notice that you're going to jump between cosine and sine. And the pattern gets a little bit more obvious. And we're not going to go past 2, because why would we, right? You rarely talk about f elements. Now again, now what can you possibly do now that we've used up a sine and a cosine? Well, you're going to have to, now remember that you're actually, if these are excited states, they have to have nodes. What does a node look like for an angle? It ends up, now you probably don't know that, you have to square the thing. So the way to introduce nodes in angular functions is to square them or multiply them. I mean, cosine squared is cosine times cosine. And for various reasons, there's some weird minus 1 there. I don't really know why. Again, I do know why. It's because that's what the solution says. Okay, now you can see a little bit more of the pattern that maybe you expected. Cos, sine, and what would you guess for the last one? Can I answer? One time someone left their phone up here to charge, and then it went off, and I answered it, and I was talking to them in the Japanese accent for like nearly, anyway. Sorry, I shouldn't admit that stuff. Okay, so what do you expect for the last one? Sine squared, right? Right, because that's kind of all right. I've got cosine squared, cosine sine. It's not going to be sine cosine because that's the same thing. So it's sine squared. And then e to the plus or minus I phi. Now m equals 2. So again, hopefully you can kind of predict this 2 phi. There you go. And again, like I say, you apply these to, you just apply these things to the miniature Schrodinger equation, the separated Schrodinger equation, and you show that it works. I'm having you do that on homework. I'll do that, a little bit of this after our test. I'm sure there's one other thing I wanted to talk about, but I just seem to be in not the best shape today, so I'm kind of forgetting what that is. Anyway, yeah, so I'm just going to drop it from there. So remember Wednesday when all of you actually show up.